Bismillah ar-Rahman ar-Rahim. We have the optimization problem of minimizing x3 minus x1. The variables are x1, x2, x3. They are distinct integers. x1 is strictly less than x2, which is strictly less than x3. Those three integers are the roots of a cubic polynomial with integer coefficients. We have an additional constraint. The first derivative of this cubic polynomial must also have integer roots. Note that if we have a cubic polynomial f of x with these roots, if we replace x by x minus eta, then the roots will be shifted to x1 plus eta, x2 plus eta, and x3 plus eta. In our case, if we have a cubic polynomial with integer roots, if we do a shift by an integer, then we will also get three integer roots. The shift is also applied to the first derivative. If the first derivative of f of x has integer roots and we do a shift by an integer, then we end up with a new first derivative that also has integer roots. What is the point of this discussion? In investigating the problem, we can focus on cubic polynomials with integer coefficients that are monic, so the coefficient of x cubed is 1, and such that x2 is equal to 0. This simplifies the problem and allows us to write f of x as x minus alpha, where alpha is a positive integer, then x plus beta, where beta is a positive integer. The three roots of this polynomial are minus beta, 0, and alpha. The objective function is alpha plus beta. Without loss of generality, we will use this cubic polynomial with roots minus beta, 0, and alpha. We minimize alpha plus beta. Both are strictly positive integers. If we expand, we get the polynomial x cubed minus x squared multiplied by alpha minus beta minus x multiplied by alpha beta. The first derivative of f of x is 3x squared minus 2x times alpha minus beta minus alpha beta. The first derivative is a quadratic polynomial, and we want the roots of this quadratic polynomial to be integers. We write down the first derivative as 3 times x minus a times x minus b, where a and b are integers. If we expand this, we get 3x squared minus 3x times a plus b plus 3ab. Now we can relate the integers a and b to the integers alpha and beta. 3ab is equal to minus alpha beta. 3a plus b is equal to 2 alpha minus beta. The product alpha beta is a multiple of 3, which is a prime number. Either 3 divides alpha or 3 divides beta. Without loss of generality, let's assume that 3 divides alpha. We can then write alpha as 3 times a positive integer alpha bar. Let's use this result here. We have 3a plus 3b equal to 6 alpha bar minus 2 beta. These terms are a multiple of 3. 2 beta is divisible by 3. So beta is divisible by 3. We can write down beta as 3 times the positive integer beta bar. If we use this in this expression here, we get that 3ab is equal to minus 9 alpha bar beta bar, which means that ab is equal to minus 3 times alpha bar beta bar. The product ab is divisible by 3. Either 3 divides a or 3 divides b. Without loss of generality, let's assume that 3 divides a. A is a multiple of 3. A can be written as 3 times the integer a bar. Let's use this here. We have ab, that's 3 a bar b is equal to minus 3 alpha bar beta bar. Thus a bar b is equal to minus alpha bar beta bar. To get rid of this minus sign, we can just define b to be equal minus b bar. Our equations now are a bar b bar is equal to alpha bar beta bar. From here we have 9 a bar, because a is equal to 3 a bar, minus 3 b bar is equal to 6 alpha bar minus 6 beta bar. Dividing both sides by 3, we get that 2 alpha bar minus 2 beta bar is equal to 3 a bar minus b bar. Multiply both sides of this expression by beta bar. We get 2 alpha bar beta bar minus 2 beta bar squared is equal to beta bar times 3 a bar minus b bar. This product is equal to a bar b bar. We have a quadratic equation in beta bar, specifically 2 beta bar squared plus 3 a bar minus b bar, all multiplied by beta bar, minus 2 a bar b bar is equal to 0. Beta bar is a positive integer. We need the discriminant of this quadratic equation to be a perfect square. We need the square of this term here, minus 4 times minus 2 a bar b bar times 2. This is 3 a bar minus b bar all squared, plus 16 a bar b bar must be the square of some integer, say n. If we expand the square, we get 9 a bar squared plus b bar squared minus 6 a bar b bar plus 16 a bar b bar is equal to n squared. To both sides, add 16 a bar squared. From here we have 25 a bar squared plus b bar squared plus 10 a bar b bar. This is equal to n squared plus 4 a bar all squared. The left-hand side here can be written as 5 a bar plus b bar all squared. Our integer variables satisfy this condition here. The square of 5 a bar plus b bar is equal to the sum of these two squares. We started with this cubic polynomial with integer coefficients and integer roots minus beta, 0, and alpha. The first derivative has roots a and b. These must also be integers. We established relations between a and b and alpha and beta. Based on these relations, we concluded that alpha, beta, and a are multiples of 3. We wrote down b as minus b bar. We got this quadratic equation in beta bar, which is a positive integer. The discriminant must be a perfect square. This led us to this condition here. A square is equal to the sum of two squares. We have a general solution for a square equal to the sum of two squares. These are the Pythagorean triples. If we start with the three positive integers, u, v, and w bar, the general solution is this expression here. Note that if we square, we get w bar squared times v to the power 4 plus u to the power 4 minus 2v squared u squared. From here, we also get w bar squared multiplied by 4u squared v squared. This bracket here can be written as u squared plus v squared all squared. Comparing with what we have, 4a bar is equal to 2w bar uv. So a bar is equal to 1/2 w bar uv. I consider here that v is strictly greater than u. The case of u greater than v gives us a solution where alpha and beta are interchanged. Using this side with that side, we have that 5a bar, which is 5 over 2 w bar uv plus b bar equal to w bar u squared plus v squared. B bar is w bar, and then we have this bracket, u squared plus v squared minus 5uv over 2. So what is b bar? Minus 3a bar, which is negative the coefficient of beta bar in this quadratic equation. This is w bar between brackets u squared plus v squared minus 5 over 2 uv minus 3 over 2 uv. B bar minus 3 bar is w bar. Then we have u squared plus v squared minus 4 uv. Let's now go back to our quadratic equation. What is beta bar? Beta bar is equal to minus this coefficient. This is b bar minus 3a bar. This is w bar u squared plus v squared minus 4 uv plus or minus. This is the discriminant equal to n squared. So here we have n. We divide by 2 times the coefficient of beta bar squared, which is 2. So we divide by 4. Since we are assuming that v is greater than u and beta bar is a positive integer, we use the plus sign. Beta bar is equal to w bar u squared plus v squared minus 4 uv plus w bar v squared minus u squared, all divided by 4. This is w bar divided by 4. U squared minus u squared, these go away. We have 2v squared minus 4 uv. This is equal to w bar 1/2 v squared minus uv. We have a bar, we have b bar, now we have beta bar. We can use this relationship here to obtain alpha bar. Alpha bar is w bar between brackets uv minus 1/2 u squared. Alpha bar and beta bar are integers. In the Pythagorean triples, v or u is odd, so to get an integer solution, we need w bar to be even. Let w bar be equal to 2w. Alpha bar is equal to w 2uv minus u squared, and beta bar is w v squared minus 2uv. Alpha is equal to 3 alpha bar, beta is equal to 3 beta bar. Then this is the solution. If we assume that v is greater than u, if u is greater than v, then these guys are swapped. We are interested in positive solutions. V squared minus 2uv must be greater than 0. So v must be greater than 2u. Because these are integers, then v must be greater than or equal to 2u plus 1. Rather than using u and v, I can write v as 2u plus m, where m is a positive integer. This is the expression for alpha and beta written using u and m. The roots of our polynomial are 0, alpha, and minus beta. We want the difference between alpha and minus beta, that's alpha plus beta, to be minimized. We want alpha and beta to be as small as we can. We choose the integer w to be equal to 1. These terms here increase with u and m. To get the minimum possible value, we set u equal to 1 and m equal to 1. When we make this choice, the pair alpha beta is 15 and 9. If we reverse this assumption here, we get 9 and 15. The distance between the maximum and minimum roots is 24. This is the minimum that we can get. One polynomial that achieves this minimum is f of x equal to x times x minus 15 times x plus 9. In an expanded form, this is x cubed minus 6x squared minus 135x. The first derivative is 3x squared minus 12x minus 135. And the roots of the first derivative, these are a and b, they are minus 5 and 9. F of x is a polynomial with integer coefficients. Its roots are distinct integers. Its first derivative also has integer roots. This cubic polynomial and infinitely many others achieve the minimum separation between the maximum and the minimum roots. This minimum separation is 24.